hit the record. We'll get going.
Okay, you're good.
Great, thank you. Good afternoon, everyone, and welcome to the Connecticut Manufacturing Internship Program webinar. We are excited today to have a presentation on applications of additive manufacturing. And our agenda for the day is on the next slide. We're going to hear from Zach Gibbons, who is our senior technical trainer and an extraordinary talent here at CCAT. We're also going to have some comments from Frank Villani, who is one of our interns this summer. Then proceed to Q&A and a fast rundown of upcoming events. And just a reminder for everybody that's on the call, if you are in a conference room with others, please drop the names of the other people in the chat because I can only see the name of someone who's logged in. And I see one name, Braden. I see your name twice. So if you've shared your link with someone, that's fine. But if the other person couldn't put their name in the chat, just so I can have attendance, that's required by our funder. And thank you. And because this is not an open webinar, but one where you would only be able to communicate any questions, please also put those in the chat. And we will get to those as Zach starts wrapping up his presentation. But we're really excited and we can move forward. Another slide. So here's Zach, as well as his contact information. So please take that down, connect with him on LinkedIn. And I'm going to turn it over to you now. And thank you so much. Really excited to hear from you today, Zach. Thanks.
Thank you, Eileen. So a little different for me doing a webinar here. Usually I'm in front of a classroom of people and we get some back and forth. So let me get some time here to talk to myself on additive manufacturing and hopefully teach you guys something new. That's the goal. So the presentation I got for you today, additive manufacturing, what 3D printing really means for modern engineering. When we hear that term 3D printing, it might mean a few different things depending on who we're talking to, our experience with it, how long we've been in industry. We're going to go through what that means today, what that looks like for overall or general manufacturing, as I'm going to put it, and give you guys plenty of examples of how it's being used to benefit parts and manufacturing processes at this point across the world. So with that, we can dive right in. So question number one, what is additive manufacturing? So, I want you guys to ask yourselves what comes to your mind when you hear the term additive manufacturing. You might be imagining some different things. Many of you may have, a desktop printer at home, in which case your familiarity with additive is actually a lot more than most of the engineers out there. One thing I have to remind myself working in the additive space is that not every engineer knows everything about additive manufacturing. So fun fact, additive manufacturing would be the industry correct term for what we historically referred to as 3D printing. So what is it? Let's add a definition. It's a manufacturing process by and large, and it builds parts layer by layer instead of removing material or forming it, much like casting or CNC machining. It comes in a lot of different shapes, sizes, materials, processes, and through the course of manufacturing history has been known by other names. 3D printing, which is probably the most common, and prior to 3D printing, it was often referred to as rapid prototyping. Fun fact of the day, I got my start in additive manufacturing next door at Pratt & Whitney when I joined the rapid prototyping group because I thought rapid prototyping sounded pretty cool. I had no idea what that meant or that I was about to be involved in additive manufacturing. So additive manufacturing as a whole, we can look at it as, by its names or terminology, but I like to kind of break it down to the basics and really talk about what I'm going to refer to as layer-based manufacturing. All right, so on the right side of the screen, we have an image of some material extrusion or filament printing, as we sometimes call it. And what is true of most additive processes, I mentioned we have a range of processes. In most of them, we're going to deposit that material in discrete layers. Right? And those individual layers, we can really start to think of those as 2D individual slices. And that's where we get those print layers that you see in that photo. Right? So if I took those 2D individual slices and started stacking them together, when we stack them at a given layer height, we really produce a three-dimensional object. And that's kind of a top-down, and this would be a side view of that actually happening with some just basic shapes. But 3D printing as a whole, we can really think of it as kind of a topographical contour of that part's surface, right? We can really kind of draw some analogy to what we would see looking at a land-based topographical map, and how we can separate that 3D geometry into those individual discrete slices at those individual layer heights, much like we have a contour spacing on a topographical map. We're really kind of printing the topography of those parts in real time. So when we hear about 3D printing or think about additive manufacturing, it usually starts with the process most people are familiar with today, and that's what I affectionately call the CNC hot glue gun, aka the desktop printer. As you're going to find out, there are a lot of different names for processes. In this case, desktop printing is actually now referred to as fused filament fabrication, or triple F. And again, this is an AM process. We're building parts layer by layer, in this case using thermoplastic filament. We're feeding that material through a heated nozzle. We're melting it. We're depositing it along a pre-programmed toolpath. And as it prints, each new layer is fusing to the material on the preceding layer. Right? So we require precise control of your temperature, nozzle motions, layer heights to achieve that dimensional accuracy. Support structure is also something we need to possibly be worried about in 3D printing. We generally cannot print in open space. We need a substrate to be able to build on top of, right? So we add these layers together and we stack them to get our solid part. Anisotropy and voids in these layers can cause defects or quality issues. We're going to briefly touch on that. So anisotropy, meaning we have different material properties in different directions. And that is true of almost any layer-based manufacturing process. When we make these parts, we're going to have differing material properties, and that just adds challenges for us as engineers, as designers. When we go to actually design a part to be additively manufactured, we need to be able to account for that anisotropy. So this is a process most folks are familiar with, aka desktop printing. But what does the reality of additive actually look like today? So to give you guys an idea, I took some highlight photos. I was recently, earlier this year, at the Additive Manufacturing Users Group conference, and just took some images from that conference that I thought encapsulate the breadth that is additive manufacturing today. What are we looking at on the screen? So this would be some polymer additive process or polymer additive parts. These were made on Mimaki's material jetting process. This is a polymer print process that can print in full color and operates very similarly to how an inkjet style paper printer works. We have inkjet style print heads that are putting down material layer by layer, just like you would print ink on a piece of paper. We're going to then, drop a layer thickness, build layer number 2, and build up the material like you see here. So a couple, we have a couple different things going on here. We have a replica circuit board printed in full color. We also have some possible medical models, right, showing, the human skeletal anatomy. And this is all printed together as one part in full colors. Still from Mimaki, some of their other display parts they had, some exploded assembly views that were encased in clear resin. And on the right side of the screen, we have an example turbine case with some differing colors actually modeling flow paths through that particular geometry. Okay, so just some examples of what we can do today. Some design contrast entries. For this one, the individual actually printed a model of themselves standing next to their printer. The printer itself is also printed. So we have a printer replicating itself in miniature form. There were plenty of examples on display of complex geometries. On the left, we see an aerospace flow path component. If we take a close look, we could see, there are things like internal geometries that would be very difficult to manufacture another way. On the right side, we have a heat exchanger. example. And this, again, just my own hand for size reference. So this would be a gyroid heat exchanger enclosed in what I'm going to call a rather small part. So very complex, very intricate geometries we are able to create with additive. Here's an example of a drone frame that was likely generated using either generative design or topology optimization. Those are two FEA or finite element analysis driven modeling techniques where we're actually using computer simulation to come up with our best guess attempts at what an ideal design might look like for a given load case. Some other examples. I'm a knife guy. I thought it was fantastic that they're additively manufacturing knives. We have some examples on the right side of the screen of suppressors from the firearm manufacturing industry, which oddly enough are ideal geometries for additive. We have internal features that would be difficult, if not impossible, to create other ways. Couple that with a lot of self-supporting geometries in the print, and we have some very printer-friendly geometries to make out of metal. And the aerospace side of things, some very large-scale rocket components from SLM on the left. We also have some copper rocket components you can see on the right-hand side. This came out of an America Makes project, all the way to some fan favorites, right? This is my personal favorite from the conference. If you're into Fallout, you already know what this is. If you are not into Fallout, go play the game, watch the show. This is a Pip-Boy. So this is one of the design contest entries where somebody actually fabricated a functional Pip-Boy. Yes, we could click through all those menu options. It was not for sale. Otherwise, I would have that today. Right? So we have a manufacturing process that exists in many different forms, many different shapes, sizes, materials we can print in. But the real question comes down to the why behind it all. And that is really, where does additive manufacturing add value? I don't know if I've covered this, but AM, that'd be the abbreviation for additive manufacturing. And much like anything else we do in manufacturing, when we're trying to actually produce parts, there has to be a value proposition as to why we're doing that, right? What is the return on investment for us spending this money, this capital to maybe purchase expensive printing equipment to make these parts in the first place? First and foremost, I would say is the ability to design geometries that we largely could not manufacture other ways, or at least not manufacture them easily. And I'm going to loop that into the term design freedom, right? So we have a whole new freedom we get with 3D printing in terms of the different shapes, geometries we're actually able to create using this printing technology. But there are a number of other ancillary benefits which might not mean too much today, in a college engineering course, but when you find yourself out in industry working for other manufacturers, things that definitely hold a little more weight. One of the biggest drivers in recent years, I'd say since the COVID pandemic, of adopting additive has been for lead time, right? So when we bring additive manufacturing in-house, let's say we're making tooling, for example, we are able to take a level of ownership over our processes that we might not have if we were using an external vendor or provider to actually manufacture those tools for us. So lead time, I'd say in the last 5 years, has been one of the biggest drivers for additive adoption for manufacturing companies. With that, we can often get a part cost reduction, right? So part cost can come from a number of places in manufacturing. There's the material that goes into the part. There's the cost of the equipment used to manufacture the part. But there's a lot of other ancillary costs we don't talk about that do drive individual part cost. Things like our upfront engineering work, right? What work did design or product definition have to do to actually come up with that design to be printed or manufactured, right? So part cost is a big one. And then, of course, material waste. One of the key things about additive that makes it different from, let's say, subtractive manufacturing is we're adding material where we need it, as opposed to subtracting it where we don't. Right? So if I'm machining a part out of a solid billet or block of material, we're going to choose appropriate cutting tools. We are going to start cutting that material away, creating chips, and removing that material until we get to our finished part geometry. In additive, we are just adding the material where we need it. So we end up with an opportunity for a lot of material savings on the waste side of things as well, depending on the actual part geometry. But I mentioned there were a number of different types of additive manufacturing processes. Fortunately, we have groups out there like ASTM who have kind of organized them for us. Right, so these are the 7 different ASTM process families. For those who are not familiar with ASTM, that's the American Society for Testing and Measurement Standards. And there are a number of different standards organizations out there that manufacturers can look to for guidance in looking to operate these processes with some type of consistency across industry. Right. Company A and company B may operate differently, but maybe they want to do some business together. We can lean on these industry standards to make sure we're at least kind of playing in the same ballpark, so to speak. And so we have 7 different AM process families: vat photopolymerization, aka resin printing. We have powder bed fusion. That is basically any process that is using a powder bed to convey the material. There is binder jetting, which is also a powder bed process, material jetting, like I referenced with those Mamaki pictures, sheet lamination, material extrusion, which your desktop printing or your filament extrusion would fall under, and directed energy deposition. So feel free after this webinar to go look up those individual processes. I don't know that we're going to have time to go through what each of them are today. And we have hybrid manufacturing on there as kind of a fun addition. And hybrid manufacturing is a newer trend, I'd say, within the last 10 years or so. We can look at machine makers like DMG Mori, who are making combination machines where we are incorporating both of that additive build capability along with, let's say, the capability of a 5-axis CNC machining center. So within one machine, we can actually build up material, machine it back down to conforming geometry. Right? So I mentioned 7 different process families, but in reality, we have a lot more additive processes than exist just in those 7 families. So if you look at this image, within each of those 7 process families, we have a range of different processes within them. Some of them are proprietary. I will admittedly say some of the machine makers have named their own process, even though a more common name works. But when you're running a business, sometimes you want to differentiate yourself from your competition, right? So we have a massive range of different processes. So when we're talking about an additive process to somebody, what is the best way to kind of describe what we are talking about? And much like Einstein standing on the shoulders of giants, in engineering, we beg, borrow, and steal relentlessly where we can, try not to reinvent wheels that don't need to be reinvented. And that's exactly what I'm about to do here. So AM in 3 questions. So the Barnes Global Advisors, they're an additive consultancy group that is partnered with CCAT. And this is something I'm borrowing from them, and it's their AM in 3 questions. So 3 questions to ultimately define or be able to define or describe any additive manufacturing process. Question number 1, what is the material and what is its form? Number 2, what is the process energy source? And that third question, how is the layer being deposited? So I'm sure from those of you who have had some access to desktop printing, we can already tell based on these images, we're talking about material extrusion. So let's use that as our example to answer these questions. So what is the material and what is its form? In this case, we're dealing with thermoplastic filament. The energy source would be a heated nozzle, right? We're using conductive thermal energy to heat up that filament within the heat break of that hot end. And then how is the layer being deposited? We're depositing material along a pre-programmed toolpath. Right, so 3 questions, we can fully describe what that process is. As an example, let's turn that to something like laser powder bed fusion, where we might be printing in metals. So what is the material? We're dealing with metal alloys, all in powdered form. What is the energy source? This would be laser energy in this case. And how is the layer being deposited? Right, so material is being spread across that entire build area by some form of a recoater blade. Right, so that process is going to spread material. Our laser is going to melt that 2D part geometry within that individual layer. The whole build chamber is going to drop 1 layer thickness and rinse and repeat that process until we actually have a fully formed part. So regardless of the process family, regardless of the material, we can use these 3 pretty simple questions to describe what is really going on in each of those additive manufacturing processes. So looking at how the AM process itself actually works, this is going to be pretty common or pretty universal to almost all of the additive processes out there. And it's all going to start with that 3D model, right? We can consider this our solid part geometry, and we often refer to this as our nominal model. We can think of this as our level of theoretically perfect geometry, right? So this is what we're attempting to print with the printer. We're going to take that 3D model, we're going to export that as a mesh file. For those of you who have printed before, you know you need an STL file or a 3MF file. Those are mesh files. And all a mesh file is doing is really representing the exterior surfaces of that geometry. And it's a distinction that we have to make. That 3D part model, when I design a part in CAD, we can go into that CAD software, we can assign a material. So once I assign a material, we can now assume things like mass, for example, of that given part. That mesh geometry is not a solid geometry. It is only a representation of the exterior surfaces, but that is what we're using to start our print journey. And these two steps are going to happen in our CAD and our design software, where we actually do the part modeling and then the file export. We're then going to take that mesh file, we're going to slice that into those discrete 2D layers that we talked about. So when we stack these layers together, the end result should be that final part geometry. Right? We're going to take our process parameters and apply them to those discrete 2D layers. We can think of our process parameters like our speeds and feeds for a CNC machining center. For desktop printing, I have temperatures I have to worry about, nozzle temperatures, bed temperatures. We have speeds and flow rates that we have to be concerned with in order to get that material, printing nicely on the print bed. Right? So we apply our process parameters, and then when we combine those layers plus the process parameters, we're going to package that together into our machine build file in our respective machine code language. Right? Most commonly, this is going to be G code. G code is, very kind of universal in terms of machine language. We have a lot of machining centers, for example, today that actually run off of G code. There are some proprietary file types when we get into the more commercial additive equipment. But by and large, if we're dealing with desktop printing or anything in that realm, we're going to be pretty hands-on with that G code. So these three steps are happening in what I'm going to call our slicer or our build processor software. They can be separate pieces of software, but at the desktop printing level, these are usually combined into one. Ultimaker Cura would be an example, or Prusa Slicer, or Bamboo's Slicer if you have dabbled in the bamboo world. Right? So once we have all this information together, we can then take that build file and send it to the printer. And then the printer is just going to execute its machine code. Right? So this is a good time. I like to point out that I love referring to additive machines or 3D printers as dumb machines. And why do you call them dumb machines, Zach? That's because they will follow pretty much any set of commands, any code we give it to run. If we have a very expensive CNC machining center and we tell the machining center to crash the tool head spindle into our workpiece as hard as it can, unfortunately, it's going to listen to us and do it. I think of machine tools as just the best pet puppy that just wants to make you happy and is going to do anything you ask of it. Same thing is true in 3D printers. If we try to tell these printers to do something that they should not be doing or cannot do, the machine itself usually does not know that, and it's going to attempt to do it anyway. So that's why we got to give it good approaches. If you live in the Thingiverse world, maybe you have a printer at home and you're just downloading files, you're basically focused on this aspect of the process. I will say that 3D modeling capability, that's kind of that next level capability in terms of your own personal capabilities in operating additive manufacturing processes, right? It's one thing being able to make the parts, it's another being able to adequately design geometries to be printed. Right. So we can look at the additive process as, kind of a standalone process when we consider the greater manufacturing process. So in the real world, we can look at the additive process as it's standalone process, but that's going to be fed by other processes within the business. Right. So we have our additive process that's going to be fed by design and product definition. Design and product definition is going to be giving me let's say those CAD models we're going to be using to set up the build file. They've designed this part to work in, either standalone or work as a, sub piece in a greater assembly. So we're going to print the parts, and then we have our parts coming out of the printer. They might need some further post-processing. And another way to refer to that would be part finishing. Right? Maybe we have critical mating surfaces on metal parts, in which case we're going to want to finish machine those mating surfaces where the two parts actually meet together at a bolt flange, for example. Right? So we oftentimes have further processing we have to do on these parts to get them where we need for use. Those parts are then going to go into our quality and inspection organization. Right? So they're going to inspect the parts for quality, make sure dimensions look good, make sure the material itself looks good, and then that part is going to enter in a service. Right? So the AM process is really just one piece of that greater process. The hard part of all of this is not the part that happens at the printer. It's actually what comes before and after that kind of dictates the success of 3D printing in manufacturing. Which brings me to what I'm going to call the most important single slide in this entire deck, and that's this right here. AM is a tool. It is not a replacement. This was a very hard lesson learned by many different organizations through many different manufacturing industries. I honestly can't tell you the many, many millions, if not billions of dollars that have been flushed down the toilet. I am not being facetious at all. Well, I guess I am about the actual flushing in the toilet, but money wasted on what ultimately ended up being bad efforts, right? So our first thing we learned is additive is not a replacement. Is not a replacement tool. It's just another tool in the manufacturing toolbox. So we must collectively shift from asking, can we print it, and focused on whether we should in the first place. And that comes back to that business case conversation I briefly mentioned. And so if it is not a replacement tool, how does it stack up against our traditional manufacturing methods? Right? So additive, what is it good at? Complex geometries, internal features, rapid iteration, but everything has its limitations, right? We're generally going to receive porous surface finish. We're going to have anisotropic material properties, right? That is not something I'm going to experience out of a process like casting in metal or injection molding plastic. So we have differing material properties in different build directions in most additive processes. When I look at subtractive manufacturing, excellent tolerances, excellent surface finish, very mature processes in that they're very learned out by industry. Right? There's not too much new we're going to learn about CNC machining at this point. Controls might become better, defect detection, machine learning might get better, but we've been doing this for a very long time at this point. But it also has limitations, significant material waste, and line of sight access. If I can't physically see it, I can't get a cutting tool to the feature to actually cut that feature, which means things like internal features are automatically a no-go for subtractive manufacturing. And then we can compare that to formative manufacturing. This would be things like casting or injection molding, very fast production rates, very good repeatability, low per part cost at very high manufacturing volumes. But we also have downsides, very high tooling costs, extremely long lead times. I'm hearing actual examples right now of people being quoted 2 years of lead time from casting houses just to get their tools in hand. And that's just to get your tools. You haven't even made your first part. So serious lead times today if you actually want to get a new part cast. But how does it compare on cost? So this is a pretty old image from Deloitte, but it still holds true today. So we have, let's see, cost per units manufactured on our vertical axes versus our units manufactured. So, as I create more and more parts, what happens to my per part cost? With conventional manufacturing, we see this nice decreasing asymptotic behavior where if we're only making one or two, the parts are naturally going to be very expensive. But if I'm making 1,000 parts, 100,000 parts, 5 million parts, the cost is going to come down significantly at those higher volumes, as opposed to that additive manufacturing, which is just kind of holding a horizontal line. And there's a real important reason for that, and that's because 3D printing is a batch process, right? Meaning I can only fit so many parts in one batch on a given machine. The analogy I like to use is Thanksgiving turkeys. Let's say you're baking a turkey and you can only fit one turkey in your oven. If you needed a second turkey, well, you either need to run a second batch or you need a second oven. You can't make that one oven do more than it's already capable of doing, right? So we get a very even 1-for-1. If I need 2 parts, it's going to cost me twice as much relationship when we look at additive costing. So additive tends to excel in high mix, low volume applications. So low volume applications where I maybe have a high variety of parts could be good for additive. Which additive is generally more adaptable to rapid change. And if I have a part redesign, I just need to set up a new build file. I don't need to fully program, a new machine code like we would traditionally do with CNC machining. Situational requirements govern the comparison between traditional and AM. One thing I love to say when it comes to cost or anything else when we're talking about additive is it really comes down to the specific part, the specific application we're talking about to actually make a good comparison back to traditional manufacturing as to whether it would be good, to move that towards additive. So what drives cost in additive? Well, looking at the process itself, so the preprint process, and these are just rough numbers, but this is still pretty true today. We have preprint at 10%. That'd be everything to get towards your build file. You have 40% of the cost wrapped up in the additive process itself. That would be the anything happening with the printer. And then half the cost of a part is coming from post-processing. That's all the finish work that's happening. Now, this is definitely going to be ring true when we're doing metal additive. We usually have significant amounts of finished work that needs to happen on these parts. So, something to note when we're doing a cost comparison, one of my first questions is going to be, have we figured out, what finishing operations we actually need on these parts? Because that's where most of the cost of those parts is actually going to come from, not the print process. Which brings me to some hard truths of additive. Overhangs in support structure. In theory, we can make any shape, but I can't print in open space. So you always need some type of substrate to print on. That would be support structure, which would be further sacrificial material. The processes are dominated by thermal physics, whether we're talking laser powder bed fusion in titanium alloy or printing in PLA plastic on your desktop printer in your dorm room, right? Process physics are still dominating that process. I mentioned the directional material properties. Tolerance is not unlimited, right? So AM, we're often printing what we call near net shape, not final shape. And that is where that post-processing comes in. If I have very tight tolerances I need to hit on a geometry, I might intentionally add material to it in the print with the goal of machining that back down to its tight tolerance dimension after the fact, right? Material properties are process dependent, from one additive process to a next, even in the same material. I can't necessarily assume that our properties of that material are going to remain the same. And economics still matter, right? We can fully optimize a bracket for additive and save weight by 20%, but that same bracket could cost, 8x more to manufacture or take significant machining, which is all going to impact that cost. So looking at applications of additive, these are a bunch of projects that CCAT has been involved with at some point. We can break down applications into categories, and I broke them down into product development, so things like concept models or functional prototypes. We can use it for manufacturing support, tooling, fixtures, patterns, molds, anything that basically helps our manufacturing process at the shop floor level. I would say this manufacturing support today is where every small business I've talked to looking at adopting additive manufacturing is looking to use it, right? So they're looking to bring in tooling manufacturing in-house. Maybe they're relying on a vendor, but they're able to print, this tool at a much lower cost, much quicker by bringing additive internally. We can, of course, use it for production parts, ideally for low volume parts, though that is changing as the machines get better and better. But we can also, redesign for things like higher performance and customization as well. Sustainment and repair, right? This is a huge area for additive manufacturing. Most folks don't know this, but when we take a company like Pratt & Whitney, for example, who is one of the world's big jet engine producers, most people don't know that Pratt & Whitney sells a jet engine at a financial loss, right? So they sell a $7, $8, $9 million engine and lose money on the sale. Their business model and where they actually make the money is in the aftermarket sustainment of those engines. So those engines might have a 20, 30-year service life, And through that service life, they're going to need multiple core rebuilds, a lot of part replacements, repairs. And this is a big area that in aerospace that additive is actually taking hold today, and a lot of development work is happening. And then, of course, a lot of advanced applications across many different industries. So looking at AM for prototyping, this one's from PTA Plastics. They're an injection molder. They were looking at improving their prototype development process to assist their design for manufacturability analysis. And they onboarded HP's MJF system, which is a polymer binder jet process. And so this just some ways this has helped them. They were awarded a $3 million order over 5 years from one customer where they were able to utilize those printers for prototyping. They've since transitioned all of their inspection, machining, and assembly fixtures, as well as the robotic end-of-arm tooling, all to additive, and they estimate their annual savings at about $125,000 or more for that. And by implementing additive, they've inadvertently freed up 650 tool room hours that they measured over a 5-month period. So they're estimating a $50,000 additional annual gross profit just based off of saving up that time in that tool room, right? So this is if we can imagine a small shop that maybe doesn't have the space for another machining center, they might have space for a couple desktop printers that could free up a couple of their machining centers, thus making them, their shop effectively larger in that same footprint. Burke Aerospace, they were experiencing high costs and lead times for metal EDM fixtures. That's electrode discharge machining. We're basically using very high current to vaporize metal and cut it. So they brought a bound metal system in process. This is a sinter-based additive process where they're now doing 90% of their internal tooling work in-house. So their traditional fixtures, a lead time of 8 to 12 weeks, cost of about $1,200 a fixture, compared to the additive solution, lead time of 10 days for the additive tool, internal cost of about $200. The result is their equipment paid for itself in about 9 months. Another example, Straight Tech LLC, a local organization using additive to make CNC machine fixtures. So now they're estimating they're saving $700 to $1,500 per machining fixture. Westminster Tool, they make medical tooling. So they were actually making these kind of tweezer-like tools out of a carbon fiber, I assume a carbon fiber nylon 11 composite, and they found it was eating away their aluminum molds. So they went to additive to reprint their molds out of an H13 tool steel, which is much more robust and going to resist that wear far better than the aluminum would. Right. Some fun stories, Leaps and Bones. So they're a local pet product manufacturing company, and they had an old machine for making their dog biscuits that was mothballed or orphaned by their manufacturer, meaning you can't get parts for it anymore. Imagine what happened if you held your car for long enough that you call up Ford and they go, well, we're terribly sorry, but we just don't have parts for your car anymore. This is effectively what happened. So CCAT was able to print several prototypes out of some carbon fiber nylon 12, which was able to accommodate their heat and strength requirements and keep their old machine up and running. I mentioned maintenance, repair, and overhaul. So this one from GKN Aerospace, where they're using directed energy deposition quite heavily in their repair processes. Fun fact for those looking at places to go within their careers in Connecticut, GKN is making significant local investments at their facility down in Newington, where they're building out a large additive facility. And I have to imagine a lot of repair work, if not production work, is coming to Connecticut through them. So just something to keep in mind for the future. This was a case study from Newton Engineering and Product Design. They were responsible for the door hinge on the containment mechanism for one of the Mars sample rovers. And their goal was to redesign through additive to optimize for part weight as well as a larger torque margin. You can see the images of that hinge bracket on the right. And they achieved a 30% weight reduction while maintaining the required stiffness in that part. Right? We look at AM for part production. Here's an example of a marine gangway. For those of you who know what a gangway is, wonderful. For those who don't, if you've ever walked on a big boat and walked up a ramp, that ramp is referred to as a gangway. right? So they were using large format polymer additive here to print this gangway, which is satisfying their ISO requirements for allowable deflection under specified loads. It has undergone testing and has since been approved by the American Bureau of Shipping for actual use in the field. Okay, and then we can use additive for part count reduction. This is the GE LEAP engine fuel nozzle, probably one of the most famous additive parts today, where they consolidated 20 parts down into one individual piece, making this fuel nozzle 20% lighter, increasing its life by a factor of 5. And at this point in time, there's probably fabricated on the upside of 100,000 nozzles. This is just an image of their catalyst turboprop engine, which they received some recent FAA approval to continue forward with the development of. And they have reduced 855 parts down to 12 parts solely using additive manufacturing. And probably one of the more famous examples, I don't know if anybody here has been following what's going on with SpaceX, but here are the SpaceX Raptor engine iterations. Right, so benefits to redesigning: weight reduction, performance improvements, lower assembly costs, quality improvements. We can see some quotes from Elon and company on the benefits of implementing additive in their in their business. And so we can see from Raptor 1 to Raptor 2 to Raptor 3, it almost looks like the engines are getting simpler. And what happened was they went to internal features to redesign their parts, so their parts are effectively pulling double duty. So that nozzle in Raptor 3 has a lot of internal conforming flow paths through the actual bell of the nozzle, and because of the way they redesigned these parts, they have since been able to remove any external hardware related to rocket cooling. Right, so what are the benefits of actually designing for additive manufacturing? That's what DFAM stands for, Design for Additive Manufacturing. First and foremost, increased design freedom and innovation, right? We can make geometries that we could not previously make. We'll get some material efficiency. Right? If I pull material out of my parts, in theory, those parts are going to be cheaper to print. We can also reduce lead time. We can use additive to shorten development cycles, again, replacing vendor operations with faster in-house operations. And sometimes we can end up inadvertently reducing cost as well. So this was a GE Engine Aircraft Bracket Challenge from 2013 that was put out to the world. This was the original bracket. And here was the winning submission from Indonesia. So through the redesign, right, they were able to achieve an 80% weight reduction without any reduction in load-bearing capacity, right? So why is lightweighting helpful to industry? Well, according to NASA, we can save a lot of money pulling weight out of aircrafts. So we spend roughly 5 cents worth of fuel per pound on the aircraft. Saving 1 pound from each flight, considering 10 million flights a year, we're at about 100,000 fewer gallons we'd be saving. If we look at the energy industry, we might be creating lighter parts. Let's say we're transporting large wind turbine, components. There's money that is spent in just the shipping of parts. Any person or any manufacturer out there who makes parts has to ship them out to a customer, to whether it's another organization who's using their pieces in an assembly, but it costs money to ship material. And if we can make our products appreciably lighter, we could inadvertently save costs just on shipping. And then, of course, the medical industry, we can start to achieve things like patient satisfaction, lightweighting, and better sustainment for casting applications, as an example. I mentioned support structure briefly. These are just some examples of how we use support structure in some processes: filament printing on the left, resin printing on the right. And the whole point here is we can't generally print in open space. We need some type of substrate to print on. I mentioned part orientation versus build layout, right? So we have anisotropic properties in most additive, using filament extrusion as our example, right? If I have tension normal to my layers, my part is going to be very weak. Whereas if I have tension parallel to those layers, our part is generally very strong. So that same part printed in different orientations could very well behave differently when we try to put that part into service. This is a bracket design challenge that I pulled from one of our training classes to show you guys. So we have a kind of generic bracket with an assumed load case, and we assume a material. And so our goal is to redesign this bracket, right? Incorporating a lattice structure, reducing material while staying below the yield stress of that material, right? So we have a current state, our current max stress from the FEA. What's that? 16 megapascals, which is pretty good right now. But how can we redesign that? Right, so this is just an example. This is incorporating some what I'm going to call advanced design software and topology, where we're able to incorporate this circularly mapped gyroid lattice structure. And in this particular example, we could in theory reduce weight by 57%. So 57% of the material that existed in the original bracket is now completely removed, and we're only increasing our stress by 13%. So again, 18 megapascals here, we're still well below that 35. That was the goal for this particular exercise. And in a different load case, we might have a different result entirely. If we pretended this was an upright bracket in a suspension system, we see almost negligible change in experience stress, even with removing I think the middle example removes 60% of the material from that bracket. Right. Which brings us to topology optimization and generative design. These are some advanced software techniques we can use today to make these kind of organic looking shapes you might see. The only difference between the two, topology optimization is modifying an existing geometry, whereas generative design is kind of like starting from scratch. We're giving the computer a design envelope that it can build within and allowing the computer and software simulations to ultimately dictate what an ideal design might be for a part. Right. So I'm currently, spoiler alert, currently working on a new additive training pathway here at CCAT, specifically focused on design for additive. And this is just a quick image example of what I'm going to be showing you how to do. Right. So on the left, we have a relatively simple, bracketed, bolted bracket assembly. And on the right, a unitized single piece redesign of what, in theory, we could possibly print to reduce weight while still maintaining, the performance requirements of that application. So that I mentioned that class was new. That will be coming out in the future. Today, these are the additive training opportunities we have at CCAT. This is kind of just the workflow to how to find it through our website. Go to CCAT US training page, additive workflows. And then if you click the registration link, it's going to show you a list of classes, which is just what you see here on the screen. So we have Additive Essentials. This is a one-day, full day long, high-level overview of the entirety of additive, what the processes are, what design for the process looks like, how and why is it being applied. We also have 4 technology-specific classes set up today, focused on polymer powder bed additive, resin printing, extrusion printing, as well as directed energy deposition in metal. One fun thing about coming to take training at CCAT is we will provide you with your very own accreditation to verify that you have been here, taken our training, and hopefully learned a thing or two. And I think, let's see, it's 12:50. That's probably pretty perfect time-wise, so I'm going to pat myself on the back with that. And then I guess take a moment to talk about our additive manufacturing journey. I guess I'll give you my spiel, and then Frank can tell you a little bit about his experience. So getting into additive today looks a lot different than when I first attempted to get into it. As I mentioned, I got into additive completely on accident. I had a choice between rapid prototyping and a quality role, and I'm sure you guys can guess which one sounded cooler to the young engineer working on the shop floor at Pratt & Whitney. So I joined the rapid prototyping group. I was immediately assigned as their process owner for about $6 million in electron beam machine melting tools. In which case we took those tools and then basically developed Pratt's first production operation and qualified their first additive manufactured production part. From there, went to work for the Swedish company who made the machines I was working on. That was Arcam. They're currently under the GE Additive umbrella today. Went from Arcam back to the Raytheon Research Center where we were doing research on laser powder bed fusion. Had a brief stint at a contract manufacturer after that, and now find myself here at CCAT, where I get to train folks on additive and talk quite a bit about topics that I happen to be personally passionate about. That's my story. I'm going to pass the mic to Frank and see if he wants to tell you a little bit about what he's been doing here in his internship at CCAT.
Thank you, Zach. So let me turn my camera on here. Hi, everyone. I'm Frank. I'm an intern here for the summer. So I got involved in additive manufacturing about 7, 8 years ago. I was in middle school and I was fortunate enough to have access to 3D printers at my school. So I signed up for a summer camp and kind of took off from there. So at the time, we had access to an industrial machine, a Stratasys, along with some consumer desktop printers, Lowesbot has 6s we had. And it really did pique my interest. At the time, I was more mechanically inclined. I've never been a big school person, so anything I could make or do outside of school was huge for me. So around Christmas time, same year, I ended up getting myself a little Creality printer. It was a CR10, and I used that printer nonstop all the way up until college. That 3D printer for me kind of set my goals of becoming a mechanical engineer. I want to know not only how to make things, but how I can make things better. And that's why additive stood out to me. It opens up a lot more possibilities than some typical manufacturing methods. So I ended up starting in school. I brought one of my printers up to school, and a lot of my friends started to gain interest in it as well. I used it for projects outside of class, projects that I couldn't typically do within our makerspace. And then from there, I got involved in a undergraduate research laboratory in which I have been manufacturing microwave optical lenses using FDM and SLA methods. So when it came time for me to want to gain some industry experience, I started to search for internships that would allow me to continue that work with additive manufacturing. So CCAT very clearly stood out. Most of the other internships would only allow me to work with 1 or 2 additive processes, whereas here I am able to pretty much sweep across the board and be able to work with equipment that I typically wouldn't see elsewhere. So when the summer started, they wanted me to pick out a project and create parts throughout the summer that could be utilized for educational demos for not just my fellow interns, but also for industry itself, so they can see what additive manufacturing is truly capable of. So I ended up taking on a rocketry project. I have always been interested in the aerospace side, so I made the goal of, let's see if he'll come in here, but I made the goal of making a rocket with as many processes as I could here at CCAT. So to start with the nose cone, I was able to use one of our metal additive processes to be able to print this nose cone tip out of Inconel 625. It's completely overkill for this project. However, it is a material commonly referred to as a superalloy. It is an incredibly high temperature metal that can resist deformation. I know a lot of jet engine manufacturers utilize it for their impellers. I then was able to use our one of our powder bed fusion methods, or SLS methods, to create some nylon components for the rocket, along with being able to use another FDM method, which allows me to lay continuous carbon fibers into, for this rocket, the fin can itself. So this rocket, even though it does fall into the model rocketry category, will be able to go about 2 miles high at the speed of sound. And I found it to be a fantastic demo. CCAT supported me on building it. So generally, overall, I've been able to access 4 or 5 additive methods that I typically wouldn't be able to get my hands on. And I've been able to use these as an example at walkthroughs of some of our clients' manufacturing facilities. What we'll do is we'll walk through, they'll run us through their current processes, and then we'll sit down with them and kind of isolate where additive manufacturing can benefit them. So overall, it's been a fantastic experience here. I really recommend to everyone out there to get themselves a little 3D printer. They're down to as cheap as $100, $150. Put it on your desk, put it in your college dorm. You will learn a lot more than you think you might. Along with that, some of these advanced softwares like topology, which was shown previously, get yourself a student license, completely free. Go play around with it. You will learn a lot, and you can make yourself very valuable in your fields. So I'll pass it back to Eileen. Thank you, guys.
Thanks, Frank.
That's awesome. So thank you both for sharing your journeys. And wow, Zach, really appreciate the deeper dive into the work that you do, what you've been exposed to, all the case studies that you shared. And I don't see any questions in the chat, but both, oh, sorry, we do have one. So is the IA helping with the designs to make this part easy?
I assume, I'm going to assume we meant AI.
Yeah, I
Yeah.
think so, but it's typed in as IA, but
I'm going
yes,
to assume
probably.
that was AI from Paul. Is AI helping with the designs to make this part easy? I'm going to say no today. So I don't have too much personal experience with the AI model generators. That said, I think there really is a fine line between what we are defining as AI and what we're currently defining as, FEA algorithms to design these parts. So we could have I don't know, a semantics debate over what actually constitutes AI. That debate aside, the software tools at large are really opening the door as to what we can model today. That bracket example I showed you where we incorporated that lattice structure, that really was just a brute force example of how we can incorporate that type of geometry, into a bracket type part. I specified the lattice, I specified its configuration. That would be much different than running that through a topology optimization or generative design exercise where the computer is actually going to use its software, the simulation results to come up with its best guess as to what that is. So software tools at large, blanket statement, are really pushing the envelope of what we can design today and how we can design it. Right? Those complex geometries, the lattice geometries, many of them I don't really know at the moment how I would go about modeling them conventionally. So a lot of these tools are definitely stepping stones in capability.
And just to quickly piggyback off of that, what you may be referring to is there are some text-based prompting AI tools you can incorporate within your CAD softwares now. I've played around with them a little bit, and they are still at a very fundamental level. You have to be very explicit and say, I want this hole centered this distance from this object and this and that. And I feel that we're currently at a point where it's easier to just go ahead and do that than to write out a whole text-based prompt to get exactly what you want. But they are starting to incorporate those tools. So I'm hoping to see at an exponential rate that these tools will improve.
Yeah, along Frank's point on the student NTOP license, before you even get to NTOP, if you're not doing a lot of CAD work today, I think that's a good place to start. It's definitely going to differentiate yourselves when you get into industry and just being able to do that. You might be surprised to know how few engineers out there are actually, truly proficient in those tools, though we may all have played with them at some point in time. So yeah, free NTOP licenses for students. Along that same line, Autodesk Fusion is a great one to start learning. You can get a free license for that as well. And I think that one's at least going to get you a little more in line with what I'm going to call a real CAD package as opposed to some of the other ones out there.
Yeah, I would certainly
Awesome.
agree. You also get with Fusion 360 all packages. Most of the companies you'll go to won't have all of the packages you have access to. So before you guys graduate, try out everything. There's an infinite amount of features. I've been using it since middle school and I still haven't discovered everything. So keep using it.
Thank you both. You're really amazing. And to everybody on the phone, I would say connect with Frank and with Zach via LinkedIn and also, through the email that we had earlier. We will be sharing out a recording of this webinar along with the last week's, which hasn't yet been posted on our YouTube channel. So we'll have those there if you want to go back to them in the future or have a friend who's not on the call today who might want to listen in on this webinar. Just very quickly, and Zach, thanks for again for moving me forward here, but we have a tour later this week, July 16th at Spiral in Killingly, to be followed by DefibTech next Thursday down in Brantford. That's a med device company. And then on July 24th, an end of summer social at Gastro Park in West Hartford. That's from 3 to 6. Food and a beverage are included. All of these events are free for the interns. If your supervisor from your company wants to attend the July 29th event, they can. I am sending them a link where they would have to pay to attend. So they have to pay, I think, $25 to come to that, but they are also welcome to join us. We will have other employers there as well. And if you want to move forward, again, all of the webinars that we had this summer are going to be on our YouTube. And then more importantly, the next slide, to your point, Zach, people can come to our training. So all of the training that Zach referred to that you could access through our training website, you can come to for $50 a day using a student discount code. It isn't an email that I've sent to all of you, but I can send it again. So if you need to ping me, please do. But that is also for both the 3D printing or additive manufacturing training courses, as well as the digital workflow, the digital manufacturing and QA and inspection courses, and the prerequisite to digital thread classes, which is digital awareness. So this is a great feature. We will be reminding your employers that they could sponsor you if they want, but that is totally up to them. Just for you to know, though, in the month of August, we are going to be starting for the digital thread classes, doing a 1 day a week pathway. So on August 5th, Wednesday, we will have the first of 3 Wednesdays of classes in our digital design series. So it'll be the 5th, 12th, and 19th. On August 6th, we'll start digital manufacturing for 3 Thursdays. And then digital quality assurance and inspection will start that Friday, the 7th, 14th, and 21st. So definitely, if you're looking at finishing up with your internship or wanting to reduce your time away from your internship and only be gone 1 day a week, but take these classes, that could be a great add to your resume. Please consider that. And again, this applies not only to the digital thread, but also to the additive manufacturing classes that you could have the student discount. Normally the classes cost $200 a day. So this is a great deal for students. You could tell other friends who aren't interns. You could also tell recent grads if you might know any or close friends with any, because they can also obtain this discount. And any questions, they can reach out to me. And that really is it for today. If you're not following CCAT on LinkedIn, I would suggest you do as you go forward. We do host events regularly. Tomorrow afternoon, we're going to be having a webinar with Siemens, and you could listen in to that. It is in a recent email that I sent out to you all. And you could also go on to our ccat.us/events website to find out. So thank you. Thank you again so very much to Zach for leading this and putting together this amazing presentation and all the details and examples. To our 3 interns at PTA Plastics, there you were, up in the limelight, work that was done before you arrived at PTA. But yes, we love our partnership with your organization along with all of the others. And we're here to help, right? Our work is here to help small and medium-sized manufacturers, both those in Connecticut and beyond. And especially for you all, thank you for being part of the internship program. I look forward to seeing you on other events and appreciate your time, Zach, and your leadership. And Frank, so very glad you're here this summer and look forward to having other people with both of your passion and commitment to the success of additive and the success of manufacturing. So thanks, everybody. Have a great rest of your day and week.
Bye, everyone.
Thank you.
Bye.